Good morning and good afternoon, everyone. Welcome to today's webinar on dynamic piping design for compressible fluid relief valve systems using IFT Extreme and CZ2. Today, Gary McLeod is the presenter for this webinar. He will talk through the webinar. During the webinar, if you have any questions for me or Gary, please type your question in the Q&A box and we will answer those questions at the end of the webinar. We will have one poll questions in the middle of the webinar, so I would really appreciate if you can participate in the poll question. Now I hand over that to you, Gary.
Oh, okay, well, thanks very much, Himanshu. My name's Gary McLeod. I'm a director of Cortex Engineering software, and we've been associated with Hexagon and AFT and also recently Honeywell in the process industry software. So today, the topic of the webinar is dynamic piping design for compressible fluid relief systems. And this is really an area that's been where a lot of progress has been made in the programming tools that are available to engineers. And so what I want to do is to illustrate this progress that's been made by looking at the combination of IFT Extreme and CZ2, as Himanshu implied. IFT Extreme is new to the market. It's a program that will provide solutions to dynamic solutions for compressible fluids. So let's jump into it. We've got a lot to do, so let's jump into it. What I want to do is to first to look at relieving a relief valve into a closed system. Now, the reason I've chosen a closed system rather than an open one or one venting to atmosphere is that it poses some interesting problems to the engineer. One of the reasons that it creates issues for the engineer is that we have transient piping pressure waves that transmit through the piping system. And these cause high pressures in some areas of the pipe and low pressures in the other. Now that, of course, leads to a force in the leg where we have an imbalance of pressures. And that force applies for a length of time that's the length of the leg divided by the speed of the pulse, which is usually the speed of sound. We also have other forces involved, like the change of momentum as the fluid goes around the bend. Now, sometimes these are difficult to handle. So the pressure wave is quite transient, but the momentum forces can stay for quite a long time. Now, to solve these problems, most engineers will just use some sort of an impulse force, apply it for a length of time, which is the length of the leg divided by the speed of sound. And that's a bit, most engineers wouldn't know it, but that's an adaptation of what we call the method of characteristics. I'll just explain that a little bit more before we go on, because it's really quite important to the rest of the presentation that I'm going to give. So if we can imagine that we have a pipe along the horizontal axis here, and we divide it up into different stations. If we have a pressure disturbance at one point in the piping system, that disturbance will propagate forward in the piping system and meet up with another pressure disturbance in the piping system that's propagating backwards. So if there was a disturbance of, say, 1 Pascal here and 1 Pascal here, they would propagate up in time, and where these two lines intersect at the slope of the speed of sound, then we'd have a net change in pressure here of 1 + 1, which equals 2 pascals. Now we can do that obviously at different stations along the pipe, and once we have our second row, we can propagate that up into the future. So that's what the method of characteristics basically is. For incompressible fluids, these lines are called characteristics, hence the name. They're straight lines, usually forms a parallel grid. It means that it's really easy to compute in a computer program, and it's ideal for systems, as I said, for incompressible fluids like for water hammer and so on. But it's not so good for compressible flow, because real gases, real compressible fluids, are highly nonlinear. And what that means is that our characteristics become curved. And the intersection points could be located anywhere in this position versus time diagram. In fact, some characteristics could end up being vertical, and they can even stack up on each other. In which case, if they do all stack on top of each other, we get something called a shock wave. Now, IFT Extreme, which has just recently been released, handles all of this really well. It's a really robust product, and the computations involved in achieving this are actually quite substantial. So AFT uses this modified method of characteristics, and it solves the transient mass flow and momentum equations, as well as thermodynamic relationships in the compressible fluid. And what this allows us to do is to calculate the transient fluid forces in a piping system for compressible fluids, which are behaving in a nonlinear way. Now, what I want to do is illustrate this with an example. It's a simple example. We have a pressure vessel with a pressure relief valve on the top, a horizontal section of pipe, a vertical section, another horizontal section into a pressure header, a flare header. So we're going to be using propylene at a pressure of 25 bars and 250 degrees C. And we're going to model this in two ways. The first way is the equivalent static method. Most engineers are probably familiar with this. Then what we're going to do is model it dynamically using xStream input and CESA2 dynamics. So before we get started, I'm going to hand over to Himanshu, and he'll answer our he'll present our one and only poll question. Over to you, Himanshu.
Thank you, Gary. So now the poll question should be coming up on your screen. So if you can participate, that would be nice. It's just to help us to collect some data. So the question is, how do you currently assess transient loads on piping systems using CESA static or CESA2 dynamics? Or we don't do analysis of transients, other pipe stress package, or manual approximation. So I'll leave that open. Okay, for a few seconds. Okay. Okay, a couple of more seconds, then we'll close the poll. Okay, thank you very much for your input. So this is the result that we have received. So we see a lot of people use CESA2 already. That's a good news. But a lot of people either use manual approximation or some other package, or don't do analysis of transit at the moment. So I hand over back to you, Gary. Thank you.
Okay, well, thank you, Himanshu. That's very interesting. Nice to see so many people using CESA2. Okay, so let's continue on with the equivalent static analysis, just to set the scene for the dynamic analysis. First thing we need to do in the static analysis is to define our loads. Now, I've shown here a pressure relief valve venting to atmosphere, but we can get a pretty good idea of what the forces might be in our piping system by looking at what happens when the relief valve vents to atmosphere. What happens is, as the gas vents, we get a reaction force. And that reaction force obviously starts off as the valve opens, maintains for a period of time while the valve is open, and then drops off to zero as the valve closes. And we have some fairly well-known formulae for calculating the reaction force, which involves the ratio of specific heats and the pressure and temperature of the fluid. But I think, as most people who would dealing with dynamic relief valve systems would realise, that's not the end of the story. We have to consider the dynamic response of the piping system. So if you can imagine, if we have a spring and mass system sitting here, the weight is held up temporarily by a cable or a string. If we cut the string, what happens is that the weight will fall down, go through the point of static equilibrium, and overshoot before it springs back again and gradually oscillates back to the resting position. Now, what this means is that the actual maximum force that the spring mass system will see is twice the actual static load. So that's what we call the dynamic load factor. The dynamic load factor here is 2. So what that means is, when we get back to our relief valve, is we have to multiply our discharge reaction force by 2. Okay, so we're now ready to go back into our model and apply these things. So the first thing we'll notice is, as the relief valve discharges, we'll get a high pressure region just after the safety valve outlet, and that will be a high pressure system. Hang on, I'll have to get my little pointer here. Okay, so we'll have a high pressure here and a low pressure there, which result in a net force in the Z direction, in that direction. We'll have a vertical force, because we'll have a high pressure at that end, low pressure there, and of course, as the pulse moves through the system, we'll get a net force in the negative X direction in that part of the pipe. So we can calculate the force in the pipe using our little formula that I showed before, and we end up with a force of about 4.2 kilonewtons. So we'll then apply that force on the piping system in our static model. And of course, we need to remember we have our dynamic load factor of 2, so we need to multiply each of those by 2. The question then becomes, how do we handle that in CESA 2? Well, the B31 code recommend that the resulting occasional stresses should be assessed in independent load cases. So what does that mean, and how do we do it? So we go back to a little illustration here. If we just look at, say, the change in momentum forces as the pulse goes through the bends, each of these change in momentum forces, changes in momentum will cause a force on the pipe. And as you can see here, all the sum of the forces is going to be 0. So if we applied those all simultaneously to a CESA 2 model, we're going to get a net force of 0 and really underestimate the response of the piping system to the pulse as it goes through. So we have to apply those independently. The way we do that in CESA 2 is, for example, in the top section of the pipe, we apply a force, and we put that into force vector 1. Anybody familiar with CESA 2 will understand that that can be applied in different load cases. Similarly, the one in the vertical section of pipe we'll apply in vector 2, and the one in the horizontal section of pipe will apply in vector 3. You'll notice here that I'm using a force of 4.2 kilonewtons here. That's just one of my preferences. I usually like to adjust that up to say the 8,400 newtons in the load case editor, but that's just my preference. One thing to note here, there's only 9 vectors maximum in CESA 2, so that really means that we're limited to 9 changes of direction in the piping system. And you'd have to be a little bit creative if you've got 10 or 11 or 18 or whatever changes in direction in your piping system. So let's go straight into the CESA 2 load case editor. In order to analyze this piping system, what we need to do is define our usual set of load cases, and one of those will be our sustained load condition here, load case number 5. We also then have our 3 force vectors that we set up, F1, F2, and F3, and you'll notice here I've put a 2 in front of them, meaning I'm multiplying that 4.2 kilonewtons by 2. Then what we need to do is to add those into our sustained load case, load case number 5. So we'll have 3 additional load cases, L5 plus L6, L5 plus L7, and L5 plus L8. Now, the code doesn't necessarily tell you to do this, but I also like to do a 4th case, which is all of those piping loads considered together. I think that's probably a little bit more conservative, and it's just something that I like to do. So we have our sustained plus F1, F2, and F3. Okay, so after we've done that, we can run our analysis, and what we see is that we get a piping stress that's 166% of allowable at node number 114. If we have a look at the output, we'll see that we have at node number 114, we have an allowable stress ratio of 166%. For those of you who are familiar with the piping codes, you'll see here that our in-plane and out-of-plane stress intensification values are for a 6-inch pipe going into a 24-inch flare header are actually pretty low. These are around about 1/3 of what you would expect from the table D values in B31.3 and B31.1. The reason I've got them so low is that I've used this FEA translation module in CESA 2, and that uses the recently released code B31J to modify those stress intensification values. If I hadn't have done that, my stress values would have, instead of being 166%, they would have been 500%. Okay, so if we go to, if we summarize this equivalent static approach, we got, in our particular model, we got a maximum occasional stress, which was 166% of allowable. And what this means is that if this was the real world and we were designing this piping system, we'd have to make some significant changes. Now, that'd result in additional engineering time and more than likely a significant additional fabrication and installation costs. So that's a good introduction, a good segue into the transient flow and dynamic approaches that we hope are going to save us some time and money. Okay, so the first thing we need to do when we get into the dynamic system is to define our loads. In the traditional approach, we just took a square wave and we multiplied that equation, that value by 2 with the dynamic load factor. But now that we have IFT Extreme, we can use it to define the safety valve characteristics, the opening time, and so on. We can define our piping system and so on, and we can use it to review the behavior of the fluid and the response of the fluid system to the rapid opening of the relief valve. And from there, we can generate transient forces on the piping and create a dynamic input for CESA 2. So here is IFT Extreme input. We can see that we have a schematic of our piping system. We have these P values in the rectangles here, the diamonds, represent constant pressure sources or sinks, and they will, we can see here that if I click on it, we've got 25 bar and 250 degrees C. All our model data has been input. We've got different wall thicknesses, different pipe sizes, pipe lengths, and so on. So that's all been modeled in IFT Extreme. If we want to look at the characteristics of the valve, we'll look at the valve opening characteristics. And if I double click on that icon, you can see here that I have a CV for the valve of 100, and I can define some transients. I can say that at time 0, we have the valve closed, that is a CV of 0. And at time of 20 milliseconds, I get a CV of 100. So in other words, it's taken 20 milliseconds to open fully. I've also defined a couple of junctions here, which is what you need to do when you're defining piping forces in xStream. And if I have a look at the general input parameters, you can see here that I've inserted propylene. You can see there's a huge variety of fluids that we can use from all sorts of Chempacks and other databases. We've got a start time of 1 second, stop time of 1, and I will now have defined a number of locations where we want to get our forces out. So I'm going from the start of pipe number 2 in this system to the outlet of pipe number 2, similarly for pipes 3 and 4. And I can also define the directions in Caesar-2 coordinates, which is important for applying the various dynamic load factors and forces that we're going to get out of this. Okay, so with that, we can run the model and see what sort of results we get. You can see here that there's quite a lot of calculations to be done, over 113,000 calculations to be done. And we've got about 1,008,300 time steps. So that's finished. It only took about 16 seconds, which is pretty good going. Sometimes they can take hours to run. And what we want to do now is to look at the graphical output just to see how this system's behaved. So I'll jump into looking at some of the pressures and flows and those sort of things in the different pipes. You see I've got 4 graphs here stacked up. I've got pressure on the top one. You can see that we have a relatively high pressure in the first pipe, a fairly significant pressure drop through that first pipe, through the valve I mean, and into the other pipes in the system. Mark number is an interesting one. We can see that on the discharge to the final pipe into the header, we've got a Mach number of 1. And then as we go back, the Mach number drops off through the system in the different pipes. We also see here that our sonic velocity, or the speed of sound, it changes considerably through the system, especially in the early phases of this, the pulse that travels through the pipe. And that's why that's one of the strengths of xStream, is that it can cope very well with those changes of sonic velocity. Sonic velocity is a function of temperature mostly, so you can see there there's a corresponding change in temperature as we move through the system as well to sonic velocity. Okay, now for the fun part, let's have a look at some of the forces involved. So these are the 3 forces sets I've defined. We've got pipes 1, 2, and 3. Pipe number 1 is the red, pipe number 2 is the blue, and pipe number 3 is the yellow. If we have a look here, we can see that got a fairly flat section where it dropped off to 0 after a fairly short time. But our first pipe has only got a maximum force of 1,800 newtons. That's considerably lower than the 4,200 that we thought we had initially. And the other 2 pipes have got around about 4 kilonewtons, which is well within the range that we thought we were going to have when we're using this simplified approach. So let's export these to Caesar-2 without further ado, and we can just simply hit export to Caesar-2. We can say that we want to export all 3 piping forces. We're going to write the data every time step, and we're going to select a time unit of seconds, and we're going to output, first of all, for a spectrum analysis. We also have the option to export a time history analysis, which we will do. So I just have to nominate a file name for to store the output data in. It takes only a couple of seconds to export. And then I'll also export a time history. This is for doing a separate type of analysis. For some reason, that changes the units to pounds. So I'm going to go back to newtons, and I'll accept nearly seconds as our time unit and hit export. nominate a file name, save, and that's it. So that's as simple as it is to use xStream. It's a very robust program, very easy to use, and yeah, it's a great little tool. So one thing that I would like to go before I move on, I just wanted to look at some slight differences. What happens when the valve closes? We're not going to actually use this in our analysis in a few minutes' time, but I just wanted to show this. What happens when the valve closes. What I did was I set up a system where we had a valve opening at time 0 and a valve closing at time 2 seconds. If you see here, there's some slight differences in the force curves that we've generated. For one thing, as the valve opens, we have a really flat section within a few hundred milliseconds after the valve opening, whereas when we have a closed system, we get a bit of a ringing. In other words, we get the mass flow or the forces oscillating in the piping system. And one of the reasons the reason for that is that if we have a look at the Mach number versus time curve, we'll see that we get a Mach number of 1 in the exit pipe into the header. What that means is we have a sonic shock or a shock wave at the header junction. And that, of course, means that no pressure disturbances in that header can get back into our piping system. Whereas once the valve closes and the Mach number drops off, we can see that we've got some significant changes in, or some significant interaction between the header and our piping system. Another thing that is interesting about this is that if we compare our force versus time graph with what we would have done in the static analysis, we have a vastly different waveform. Apart from the obvious, which is that the transient flow has 0 force for quite a considerable time, we also have this second pulse. Now that second pulse is very significant in that it can increase the forces, the response in the piping system markedly. To illustrate that, if I show you here, if we have a first pulse coming through, we can see that the system response rises to a 2, so we have a dynamic load factor of 2, as we would normally expect. But as the second pulse comes through, it actually reinforces the response of the system to the first pulse, and we actually get a dynamic load factor of 4. So xStream input coupled with Caesar 2 dynamics will handle all of that automatically, whereas the traditional static method can really underestimate that response, and the engineer has to be really well aware of what that situation is. Okay, so that's just a caveat that I thought we should move into before I go into the dynamic stress analysis from the single opening pulse. Okay, so we'll start our dynamic stress analysis in Caesar 2 now. Before we do, I'll just review some dynamics basics. We normally cover all of this in our Caesar 2 training that we offer. And for those of you who are unfamiliar with the concepts here, please bear with me. I'll just give a little bit of a revision to give you the basics. Those who are familiar with it, all of this will be second nature. So dynamics is, some of the important things about dynamics are the natural frequencies and mode shapes, that we have a load participation factor and dynamic load factor, which we've talked about previously. So what do I mean by all these things? Well, the natural frequencies and mode shapes are particular to the piping system. Here we have an output which shows the shape of these things. So we have a first mode shape associated with our first mode of 1.5 Hertz, and you can see that we have the bottom elbow there waggling backwards and forth. Our second mode at about 2.5 Hertz is that horizontal section of pipe moving backwards and forwards in the X direction, which is where our third pulse, the third pipe force is applied. As we go up into higher and higher modes of oscillation, we can see that we're getting weirder and weirder shapes that are being invoked at each of these different frequencies. So we could keep on playing with this and going up into all sorts of different mode shapes. But the important thing here is that each of those modes acts independently. And what do I mean by that? Well, if I just use so instead of a pipe, I'll use a cantilever as an example of an oscillating system. Each of these modes is independent of each other. Now, if I apply a force to the pipe, we can see that if we apply it in this location, we'll see that the first mode will be activated far more than the second mode, which is, that's a node point for the second mode. So the first mode will have a high participation. Second mode will have 0 because we've activated it at a node. And the third mode will have a slightly reduced, or medium sort of reaction. So that's the mode participation factor. The third thing is the dynamic load factor. Now, the dynamic load factor that we calculated in the first few slides was based on a force that was applied and stayed applied for a long, long time. If we reduce the amount of time that the force is applied, what we will see is that the dynamic load factor will change, and it will depend on the natural frequency of the piping of the oscillator that we're talking about, the independent vibration mode that we're talking about. Now, this dynamic load factor for each mode depends on the force time profile, in other words, this, the different shapes of the pulse, and the natural frequency that we're considering. So we get the force time profile from xStream and the natural frequency response from Caesar2. And one last recap is we have the effective dynamic force is going to be equal to the maximum force in our pulse times the mode participation factor times the dynamic load factor. So that's for each independent node. To illustrate that, let me show you this. This is a bit of a skip ahead to the dynamic load factors that we'll calculate, that Caesar2 will calculate for that input that we just generated from xStream. You can see that we've got 3 different curves, 3 different pipes. The first one is this blue one is the short pipe at the top. Then we have the vertical pipe in green and the long horizontal pipe in red. Now each of the, so this is frequency along the bottom. That's frequency of the natural frequency, and this is the dynamic load factor on the vertical axis. Each of these dashed vertical lines is a natural frequency of a particular mode. So the first mode of vibration for the piping system has effectively got a dynamic load factor of less than 0.2, which is significantly less than 2, obviously. And as we go into each of these different natural frequencies, we see that we get, in this particular case, we get increasing dynamic load factors as we go up through the various modes. We can do, and we can see that similar same thing happens to each of the force sets in the different pipes. So if we have a closer look, what we see here is that there's a significant bunch of these dynamic load factors that are significantly less than 2. And when we couple those with a mode participation factor, which could be as low as 0, we see that there's a really good prospect that our dynamic analysis is going to give us lower stresses than the equivalent static approach. Excuse me. Okay, so let's see how Caesar2 handles this. First thing is to import the force sets into Caesar2 from IFT Extreme. So we jump into interfaces, jump into the AFT interface, and we can now browse to the file that we saved previously, which is this one. We can input that into our Caesar2, and we can, if we highlight these, we can nominate the nodes that each of these force sets applies that. So we've got pipe, we've got P1, P3, and P4 there, designations from xStream. And we can nominate them at those different nodes. We can nominate a different number of points in the curve that we want to generate, and a frequency cutoff. I'm just going to accept the defaults there. It takes a little while for CESA2 to generate this. After all, there are something like 1,300 points in each of those force curves, and we're doing it 20 times for 3 different nodes. So yeah, it takes just a little bit. It takes actually more time to do this than it did the calculation in xStream, which is not normally the case, by the way. So at the end of this process, it's going to ask me whether I want to set up the CESA2 input, CESA2 dynamic input. And I'm of course going to say yes, because that'll set up most of this stuff automatically, so that you really don't have to think too much about doing much else. It'll do all that automatically for you. Okay, so yes, I'd like you to please set up the dynamic input for me. And I just need to select the CESA2 file that I want it to apply to, save it, and we're done. So what we need to do now is to go into CESA2 dynamics and see how the dynamic input has been set up. So here we have our the first tab here is showing the 3 dynamic load curves. So this is in fact the DLF portion of the situation. If I each of these was going to be sorry, that's the dynamic load curves that we're talking about. The second set here shows the maximum force in each of those pipes. You can probably recall what they were. It tells us that they're setting up separate force sets and applying this to different nodes. So that's really defining the mode participation factor, along with the direction that you can see in the column just to the left of it. That allows CESA2 to calculate the mode participation factor automatically. So from those, we set up our load cases. We set up just the load case with just the force, the dynamic force from in each pipe alone. So we've got 3 of those in pipes 1, 2, and 3. Then once we've done those, what we want to do is to create our static combinations. So this is where we're saying that we want the sustained stresses combined with the occasional stresses from load case in pipe number 3, pipe number 2, and pipe number 1. So I've got 3 load cases there for pipe 3, 2, and 1. And CESA2 sets all those up automatically. But as I said to you, I like to have an additional load case where I combine the sustained stress with each of the 3 piping forces all in the one load case. So I'll just add all those together. As you can see, it's pretty easy to do. And that's all the load cases I need to look at. There are no lump masses and no snubbers that we need to worry about. And all of our control parameters have been filled in for us. So as you can see, if I didn't need to put in that 4th load case, I didn't need to change anything. So we hit the run button, and we can see that CESA2 is churning through the calculations, calculating all natural frequencies and so on. And we'll pop up with the dynamic output. Now, so we've got these 3 top cases are just the forces alone, calls them shock cases. Then we have the 4 combination load cases that we set up. So I want to look at the stresses involved here and create the output, please. So we can see here that for the combination 1, which is the sustained plus the loads in the first pipe, we get a stress of 28% of allowable. If we move to the second combination, which is the sustain plus the second pipe, we get 38%. And if we move to the third pipe, we get 82%. And if we look at the combined, with pipes 1, 2, and 3 all combined together, we get 86.6%. So that's pretty good. We've actually at least halved the stress by the equivalent stress method by looking at the dynamics and getting more precise load data and more precise stress analysis too, I guess. That's great news. So I said previously that we wanted to look at the time history analysis as well. This is very similar to the spectral approach, which we've just been looking at. The difference is that CESA2 actually solves the equations of motion here in time rather than the frequency domain, and it will calculate for each milliseconds that it moves along, it will calculate the stress in every part of the pipe, and it will then collate work out what the maximum stress is and report that if we wanted to. So I quite like this. This is a bit of fun. This is really a slow motion view of what happens when the pulses hit the pipe. As you can see, the pipe gets hit with the first series of pulses, and if we stop it around about here, we can see that there's been a lot of deflection caused around that point. The piping system has moved to the negative X direction quite substantially, and we've generated a high bending moment around that connection in with the header, and that's exactly where the stress is. We could watch this. I get fascinated by watching this, and it's all good fun, but I guess we have to move on and look at the results here. As you can see, you get some fairly weird deflections in the pipe. So this is, as I said, this is CESA2 will calculate the stress at every millisecond or whatever the time difference is, time step is, for the pipe over that whole period that we nominated. And so you can see here, I have a combination load case, which is the maximum response, and I can look at the output and find out what the maximum response was. Okay, so here we can see that in real time, the maximum response was 79%, 78.9% at that same node. And if we pan down into the output, we can see that that response of the maximum stress occurred at a value of about 165 milliseconds. You can see it there. So it was 165 milliseconds. You can see here at node 112 that the maximum response wasn't 165 milliseconds, it was 555 milliseconds. So as I said, these results are collected by CESA2 and reports the maximum that it sees over the time period. So that result there of 79% odd verifies really what the dynamic spectral analysis was saying. The spectral analysis is probably a little bit less conservative, or sorry, more conservative than this time history. Time history is really good when you really know what the profile of your force versus time looks like. If you're not so sure what that looks like, then the dynamic approach, the spectral approach, is the best. Okay, so now we're looking here at the summary of the stress system results. Equivalent static was 166%, dynamic spectral 86%, and time history was just under 80%. So the result the reason that we have these results, of course, is because the equivalent static method is limited by non-realistic dynamic force definitions. And that leads to a relatively inefficient or inaccurate model. And one of the other limitations of the static method is that we, in CESA2 at least, we're limited to 9 forces or 9 different changes of direction. In dynamics, the IFT Extreme provides a much more precise force definition, and it takes into account the nonlinear fluid behavior, variable speed of sound. It can include shock waves, momentum forces on bends, pipe friction, all sorts of other things. And of course, C2 dynamics provides a much more accurate dynamic piping response. AFT interface sets up all the dynamic input for you. You don't have to worry about that. It allows for unlimited dynamic forces to be input, not just limited to 9. And it can, C2 will accurately assess the load participation factors and the dynamic load factors. So overall, it provides a much more realistic and more accurate dynamic response. So thank you for bearing with us, ladies and gentlemen. We have now reached the end of the formal presentation, and I'll throw this open to questions. In the meantime, if you have anything that you want to get in touch with us, here are our contact details, and we're more than happy to help at any time. Okay. Himanshu, are you there?
Yes, I am. It was very interesting webinar, Gary. Thank you very much for the presentation. We have a few questions from our attendees. We'll try to answer as much as we can, but if just in case if we are not able to answer your question, please drop an email to us, support@cortexsoftware.com.au as displayed on the screen, and we'll get back to you with definite answers. So you got a couple of questions here, Gary. If you can see your Q&A box, otherwise I can read them out. So I got a one from one of the attendees. Does the Extreme covers many different type of control valve trims, such as multi-drag, multi-holes, multi-path type, where kinetic energy across the trim is dissipated, producing lower thrust force? Yep, you mute, Gary, if you're trying to speak.
Oh, I beg your pardon, I was muted. The short answer to that is it not out of the box. It has valves that you would need to manually input CV values and those sorts of things. So short answer is not out of the box.
Thank you for that. We have a couple of questions that are related to demo. We won't be able to do any further demo today, but we are happy to organize one-on-one demo. So if you have requested for any features to be demonstrated, we'll get back to you with that and probably organize one-on-one meeting. So got another one, Gary. Does AFT system analysis just covers compressible fluids or other fluids as well?
AFT Extreme covers compressible fluids. For incompressible fluids, you would use AFT Impulse. They're two complementary products. I guess you could possibly model a non-compressible flow in Extreme, but I haven't tried it.
I have another one. How will you consider the effect of friction?
Friction is covered in the AFT Extreme. I think that's possibly what this question is referring to. AFT Extreme will cover the effect of friction in the momentum equation, fluid momentum equations, and the pressure losses through that. With the fluid moving through the pipe, the friction on the pipe walls, for example, will be taken into account in that calculation. It's a very detailed calculation. It includes to do the calculations. Extreme must include thermodynamic functions, changes of state, or not changes of state, but state equations and those sort of things. And friction is one of them.
Thank you for that. What is better, spectral analysis or time history analysis? Okay, well, it really depends.
Dynamic, if you really know what the time history looks like, if the shape of your pulse, if you really know and you're certain of that, I would say a time history would be better. If you're a little bit uncertain, then the spectral analysis works really well. In fact, that's what most engineers would tend to do. It's possibly the most versatile. So yeah, I would tend to use, and look, if you've got Xstream and Caesar 2, you can do them both straight out of the box. You know, you can compare one with the other. So it's a matter of personal choice.
Okay, thank you for that. What about two-phase flow?
No, at the moment, Xstream doesn't handle two-phase flow, and it only handles a single compressible fluid. So mixtures of gases, for example, it doesn't do at the moment. But this is only the first release, so we're hoping that will happen in future releases.
Thank you for that. One more question. So there are many questions people have. So what we'll do is we'll try to reply them by emails after the webinar in the next coming days. But I'll take one last question before we conclude the webinar. Can xStream analyze systems with branches and other components like compressors and turbines, etc.?
Oh yeah, absolutely. Yeah, that's one of its strengths. It can handle multiple branches, different pipe diameters, and so on. You can model control valves. You can set, for example, a system up which will in the program you can model it so that if a pressure in a certain location gets high, then a valve will close, and then xStream will calculate the resultant shock waves going through the system. So it's really versatile. So yes, it's a network program basically. And of course, as you get into more complexity, the computation time can get quite high. For a really complicated system, it might take hours or even a day or more to come to a final result.
Thank you very much. I hope everyone found this webinar very insightful and helpful. We'd like to take this opportunity to thank everyone for joining the webinar. As a show of appreciation, we are happy to offer you 5% discount on perpetual licenses if you purchase any software before 31st of July. I hope you're having a great day, and we'll send you the recording of this webinar via email. So that email will contain a link that will allow you to view the recording of the webinar. Thank you very much. And once again, if you have any questions, please drop an email to us and we'll get back to you. Sorry, Gary?
Oh, sorry. One last thing. Yes, we will, because there are so many questions, we will collate them and send that off with our email as well.
Yep. Wonderful. Thank you. Thank you very much. Have a nice day.
Thank you, gentlemen and ladies.